Hi folks, and thanks for joining me. You're looking at a tuned circuit. You can see my transistor radio here, my inductor or loop antenna here, and my tuning capacitor here. So again, a tank circuit, resonant circuit, LC circuit, however you want to refer to it as. And as I tune the tuning capacitor back to the point where we are resonant, you'll hear the local station here, the signal strength actually increase, which is around 1000 kilohertz. So you can see how that improves the signal strength. I had someone reach out to me and ask me, how do you calculate the frequency? And there's a real simple method. I think I've demonstrated this before in some of my videos, but thought I would post this by itself just to show the simple math. Let's look at the most common formula for calculating the resonant frequency. Again, we take 1, we'll divide that by 2, we'll multiply that by pi times the square root of L times C. What makes this formula a little more difficult, you can see the frequency comes back in hertz, and we're not typically working with that. And you'll see the inductance comes back in henries, which is kind of odd as well. And then capacitance comes back in farads. That's not what we're typically used to working with. So we can break this down and simplify the formula. So some smart folks actually took the formula and changed it to have a constant. And what they're doing is, if you look at this, L times C times frequency squared or by itself will always equal 25,330 and some change. We're just rounding to 25,330. So we'll use that as our constant. We can plug that in, rearrange the formula, and use that in every equation to be able to calculate the inductance, the capacitance, and frequency. Let's look at those examples. So breaking this down again to simplify things, you can see the frequency will be equal to the square root of the 25,330, and again that will be our constant that we'll use going forward. We'll divide that by L times C. And what makes this simple, you can see L will be in microhenries, which is what we're used to working with in the AM band, capacitance in picofarads, and the frequency will come back to megahertz, which is a lot simpler to work with, of course. Let's plug this into the calculator and look at one of the examples. I have the formula stored in my calculator to make it simple for future recall. Again, the square root of that 25,330, which is the constant, 220 represents the inductor in microhenries times the capacitance in picofarads. That being 100 gives us 1.073 megahertz. So it works out really well and simple to use. Let's look at the rearranged formula for calculating capacitance. Again, we're working with that constant, that 25,330. We're going to divide that by L, our inductance. We're going to multiply that by the frequency squared, or by itself. And again, the beauty of the formula, we're working in microhenries for the inductance itself, and the frequency we're working in megahertz. To simplify things, and capacitance will be in picofarads. Let's look at an example in the calculator. With everything plugged into the calculator, the constant, the 220 representing the microhenries, 1.073 megahertz, you can see it gives us 100 picofarads. Let's look at the inductance example. As in the previous examples, we're leveraging that constant of the 25,330. We're going to divide that by the capacitance times the frequency times the frequency. And again, the beauty, the frequency being referenced in megahertz, and capacitance here in picofarads. And of course, L is going to come back to microhenries. So with everything plugged in, the constant there, dividing it by 100 picofarads times our 1.073 megahertz squared, You can see it gives us 220 microhenries. So again, don't let the math out there intimidate you guys. An easy, simple method to do the calculations. Thanks for watching.